Hey, it's me, Destin. Welcome back to Smarter Every Day. So in the last episode, I explained that it's not always the most athletic team that wins in sports. Sometimes it involves the physical manipulation of objects. So sometimes it's the most intelligent team. So today, on Smarter Every Day, let's take a look at the physics of curling. Okay, before we watch some curlers, we need to learn the basics of the sport. This is the curling sheet, and the circles are the house. The goal is to get your team's rock closest to the button. There's 4 people on each team: the thrower, the sweepers, and the skip, who's in charge. Each team has 8 stones to throw, so each person throws 2. They alternate with the other team, so there's a total of 16 stones thrown. The very last one is called the hammer, which is a major advantage. Do you have any idea how difficult it was to find a curling stone in Alabama? It is really hard. Anyway, so I know what you're thinking. Curling's like the caveman sport, right? I'm going to slide this rock on ice, and I'm going to hit another rock, and we're just going to try to out-rock each other. But oh no, it's way more difficult than that. In fact, there's so many things I had never even considered until I took a closer look at how this works. For example, the simplest question of them all: what makes a curling stone curl? Okay, let's pretend for just a second that this isn't my coffee table. It's actually a curling sheet. So we know from watching TV that when a player is back here at the hack, which is where they start, and he pushes it toward the house where you're at, which is the bullseye on the ice, as he rotates it or spins it counterclockwise, it'll curl in the direction of that rotation, right? Now, my assumption is that it has something to do with this, which is called the running band. You'll see the bottom of the curling stone is concave, but there's this circular frictional interface that interfaces with the ice. So we should be able to model a circular frictional interface of a moving sliding object on a rigid surface, right? Which is this, a glass. I'm going to take this circular object, I'm going to put it down on the low friction surface, I'm going to push it towards you and spin it and expect a curl in the direction of rotation. Let's give it a shot. But I don't see that. Let's try this again. Set this down, push toward you, spin it, curl. Here we go. No. It curls in the opposite direction. This is actually what's really confused scientists for a really long time. That interface of a normal moving, sliding, spinning object on a rigid surface behaves completely different with normal objects than it does with a curling stone. There's something magical happening right here on this running band between the stone and ice. So clearly the next step is to go find us some ice. I wet my pants. Let's try again. Oh man! So the curling stone goes in the direction of rotation, but the cup goes opposite, which I can understand because as it's decelerating on the table, it's trying to tip over, causing more force on that leading edge of the cup. So when it's spinning, it's pushing against the table with its leading edge. That makes sense to me. So let's go to the curling club in Milwaukee, Wisconsin, and see if they can teach us something with prepared ice and skill, most importantly.
We are at the Milwaukee Curling Club. We are located at the fairgrounds in Ozaki County. This club is the oldest continuous curling club in the United States.
Before a game can be played, the ice has to be properly prepared, which is a science within itself. If a stone rests on flat ice, it creates a lot of contact friction, which makes the stones run slowly. Curlers use an intricate technique called pebbling to decrease the friction of the stones on the ice. Deionized water that's been purified by reverse osmosis is sprinkled onto the ice in a very specific way and allowed to freeze. Here you can see Jay pebbling the ice by swinging a sprinkler nozzle back and forth. You can't imagine the amount of variables that have to be controlled during this process. Number of arm swings, how fast he walks, humidity, the difference in height between the tank and the sprinkler head, the temperature of the water. Yeah, it's pretty crazy. After pebbling, they use a blade to nip the top of the pebbles off to create a smooth, uniform running surface. Because there's more pressure on the tops of the pebbles, there's more friction melting, which causes less friction, which leads us to sweeping. Before I researched curling, I thought the sweepers were somehow increasing or decreasing the friction on one side of the stone or the other and making it curl. I was absolutely wrong. The sweepers actually sweep in order to heat the ice up and make it curl less. If you threw 2 stones exactly the same and you didn't sweep one but you swept the other, you would find that the swept one would go straighter and farther. This is a scanning electron microscope image of a pebble on the ice. You can see that it's been nipped on the top so it's fresh. This, however, is an image of a pebble after it's been swept. You can plainly see that there's grain boundaries from where it melted when it was swept with a broom. That thin layer of water that forms acts as a lubrication lubrication barrier, reducing the friction and allowing the stone to travel farther and faster. So this is where it gets interesting. So we're trying to figure out why the curling stone curls, right? So I look around and I find the international experts for curling physics. I find a guy in Canada and I find a team in Sweden, and so I start reading all their papers. Turns out these guys are not even close to agreeing. It's really interesting. In fact, they've never even communicated with their voices. They only communicate via technical paper. Fascinating. I call the guys up on the phone and I have like an hour-and-a-half conversation with both groups trying to understand what exactly is the mechanism. Harold Nyberg at Uppsala University in Sweden explained something to me called the scratch theory. Visualize a stone rotating and moving down the ice. Now think about the running band and what the scratches that would make look like as it goes down the sheet. The edges of the running band would make this really awesome overlapping pattern as it slides down. The Swedish scientists say that because the rough spots at the rear of the band have to hop over the scratches created by the leading edge of the running band, this will induce a force on the rear of the stone, making it curl in the direction of rotation. They claim to prove this by showing images of pebbles that have been scratched at an angle after the stone slides over them. They also did an experiment by scratching ice really deeply with sandpaper at 2 angles and pushing a stone across the scratches without rotating it.
Och nu samma experiment med den polerade stenen. Kommer Harald.
Pretty convincing, right? Not so fast. Dr. Mark Shigalski at the University of Northern British Columbia in Canada once threw a stone with a polished metal running band which doesn't produce the same type of scratches. He observed that it curled like a normal stone by throwing it on freshly pebbled ice. Dr. Shigalski believes that the mechanism is something called asymmetric friction melting. When the stone travels over the ice, the friction heats up the ice and melts it, creating that lubrication barrier that we discussed earlier. He believes that there's more frictional wetting on the front side than the back due to the rock tending to tip over, just like the cup did in our earlier experiment. Another possibility is that because the side of the rock that's advancing moves faster relative to the ice than the retreating side, it could be creating more lubrication. You can visualize this by looking back at the difference in the contact patterns. This additional relative motion would create more frictional heat up on top, which would melt more ice. This water could then be transported forward by the rotation and lubricate the leading edge of the band more than the rear edge. That forward tipping of the rock, or the water transport theory, pushes the rock into the direction of rotation. Both scientists are convinced that their theory is the dominant mechanism taking place at the back of the running band, but they agree, however, that more work still needs to be done. Personally, I don't think either one of the theories can stand up to all the questions on its own. I think the ultimate model might be a combination of both of the theories. Dr. Shigalski believes there may even be 1 or 2 other mechanisms at play here that would help describe the mysterious motion of the curling stone. Who knows? What I do know, however, is that the nations that have scientists researching the physics of curling are the same nations that most often have Olympic athletes on the podiums for curling. Hey, I have a huge announcement here on my way home from work. I'm not sure if you can tell, but these videos take a lot of time and effort. Yeah, you can. You're smart. You know what I'm doing here. You know how there were 2 different experts for curling, right? And I consulted them both to get the best idea. Well, I've done the same thing for something else. Jack Conte from Patreon and Hank Green, co-founder of Subbable, have created 2 different platforms that content creators like me can use to try to generate support for what they do. Now, the idea is if you enjoy and place some kind of value on Smarter Every Day, that you can voluntarily, I'm not saying do, but you can voluntarily decide to assist what I do. Anyway, so you can go to either one of these pages, Patreon or Subbable, and there's all kinds of different perks on there. There's ways to reach out to me, there's posters, there's all kinds of stuff, infographics. So Patreon is a per video model and Subbable is a per month model. Now, I didn't know what would work best, so I contacted both of these guys and decided to test it for myself to see which one works the best for Smarter Every Day. Anyway, you can test them and see what works best for you. Anyway, I'll leave links to the Patreon and Subbable Smarter Every Day pages, and if you would be willing to support Smarter Every Day, that would be awesome. It would make my life better because I can streamline my workflow and probably be a better dad because I might have a little more time. Anyway, I'm Destin. Thank you for even considering that. Subbable and Patreon, Smarter Every Day. I'll leave links here and in the video description. Thanks. Bye. You're trying this at your house, right? Oh. Crap. broke it. Don't tell on me. In physics, there's a principle called the conservation of momentum. So if momentum is mass times velocity, and the curling stones all have the same mass, you can assume that it's velocity that's conserved. For the most part, the forward velocity of the stone just before impact is going to be equivalent to the forward velocity in the system just after impact. This works for both the x direction and the y direction. Since there's no sideways velocity before impact, the lateral velocity after the impacts has to equal out to 0. Isn't that cool?